Okay, so good evening. This is the 8th tutorial session for the NPTEL course on finite element modeling of welding processes. In our session today, we would be a little bit discussing about the basics of petsc package and and we will be discussing certain research papers in the current research papers in the area of FEM for welding processes. So at first, what I'll just open this page for documentation page of petsc library. So petsc is a numerical package for performing parallel linear algebra computations, and it has been around for quite some time. It's originally written in C++ and other such languages, but primarily in C++ and also interfaced with Fortran for certain algorithms. And so petsc4py is the one package we'll be just taking a look right now. So that happens to be a Python wrapper, which ultimately links with the C++ backend of petsc library. So what we'll do is let's start writing certain simple examples, some simple problems, but we'll do in petsc4py, which is the Python equivalent. So I was just searching here petsc4py, and we'll just take a look at some of the. So petsc essentially stands for Portable Extensible Toolkit for Scientific Computation, and it's a collection of data structures and routines for parallel computations of certain linear algebra problems, and it uses MPI standard for all such parallel communication which goes on the backend. And so what we'll do is let's take some. I think they have some very good resources on this. Maybe I'll just open this tutorial itself, the GitHub version. Yeah.
Are we doing petsc for Py, or are we doing petsc using C++?
No, petsc4py will do, yeah, because ultimately petsc4py is Pythonic interface, right?
Yeah.
So it's like at the backend. Yeah. It what it does it just interlinks what we have written in Python, then it will construct the equivalent C++ code in the background. It's essentially a wrapper, yeah. We write something and then they will call the So it's a petsc is designed to be as easy as possible while it's still delivering the performance expected for high performance numerical codes. Moreover, a careful design allows advanced users to have detailed control over the solution process. And petsc provides many of the mechanisms needed within parallel application code, such as simple parallel matrix and vector assembly routines. So solving say some of the say examples that was present, right? Say solving. So we use the what you call construct, say vec. It implies distributed vectors. Mat implies distributed matrices and matrix operators. And KSP happens to be the happens to be the Krylov subspace methods, and PC is the preconditionals and direct solvers. And DM is distributed mesh, DMD is structured distributed mesh, SNES is one such collection of methods which are essentially Newton-like methods for nonlinear systems. TS, yeah. And then TS is time integrators and pseudo-transient continuation methods. So we'll just take a look at some simple problems. So say the Laplacian operator appears in PDEs that describe many of the conservation laws of quantum mechanics. In its simplest form, Laplace equation, the operator appears as a homogeneous potential equation minus Laplacian of U is equal to 0. And in homogeneous counterpart is minus this one, Laplacian U square is equal to F. So here, say we will select the second order finite difference approximate to the solution and source and Laplace operator, right? So in this case, we will have Laplacian of U. So A will So in its discrete framework, right? So Laplacian is discretized to give something called A matrix. Will be the discrete operator, and X will be the U which we are trying to determine. So U is the continuous version, and then
by the way, it's actually stuck. Your screen stuck with overview. I don't know if you know if you're sharing it or not.
Okay, still stuck. So maybe I'll just switch off the camera. I think
Yeah, let's do that.
Yeah.
It's stuck at the presentation. So overview basics of petsc package. That's what I was thinking when you change.
Okay, now.
No, it's not. Just shared it.
Okay. Is it shared now?
Yes, now I can see.
Okay. Yeah, so I'll just repeat here. So we are essentially trying to solve this Poisson's equation. Laplacian of U minus Laplacian of U is equal to F. So we construct a discrete version of the problem, which is so it in this case, X is a discrete analog of U, and B very much is a discrete analog of F, and A is the matrix operator, which is formed upon discretization of this Laplacian operator, isn't it? So this gives us a system of Ax is equal to bit. Ultimately, so PET-SC's work is essentially to solve Ax is equal to B.
Yeah.
So yeah, and here what we can clearly say is X is the X is a vector. So in PET-C language, it will be vec object, and B will also be a vec object, and A happens to be a matrix, a mat. So mat, as per PET-SC documentation, it's called, it implies distributed matrices and matrix operators, right? So PET-C mat object is a generic discrete linear operator. Layout is compressed. So this is also one thing that layout is. So the what you call sparse, since A matrix is usually sparse, right? For many such problems. So, and you know that to store a sparse matrix, there are multiple different methods. So ideally, we only want to store the non-zero elements of the matrix. So one such approach is what we call as CRS. CRS is compressed row storage. So here what you do is in CRS that you just keep indexing of all the elements row wise, and just what we call by default you assume that what you call there is no such row, or maybe I think I should explain in Node, right? I think that will be a better way. So I'll just maybe I'll just share my other screen. Just a minute. Huh?
Okay.
It appears I'm unable to share. Maybe I'll just share something on here itself on a separate web. So CRS happens to be one such popular sparse storage approach.
So does it resemble any kind of FEM or finite difference method?
No, these are just ways. Yeah, these are just ways of storing matrix.
Okay.
Yeah, to save. Yeah. So say we have such sparse matrix, right? So this is one such sparse matrix, isn't it? Despite the size being 5 cross 5, 25 elements. But non-zero elements are only 9 in this case, say. So it's like, why to store all zeros, right? So what we do is we want to store this in a much more efficient manner. So there are multiple different ways. So even in this case, like this is the graph of a sparse matrix. So these black squares, they indicate that those are non-zero values, rest are zero. So you can clearly see, right? The number of non-zero values are very less compared to the zero values.
That's what sparse is, yeah.
Yeah, that's what sparse essentially means. Yeah. So how do we store it? So one such very popular one is CRS, which is compressed row storage.
Okay.
So in this case, what we do is say you have a matrix M. Right. Okay. So what sparse matrix M? So we use 3 one-dimensional arrays to store it. In this case, what we do is, now let's just see. So suppose we have a sparse M cross N matrix in row form. Then we use 3 1D arrays, V, col index, row index. So let N and Z denote the number of non-zero entries in M, right? Because N and Z means number of non-zero elements entries in M. So arrays V and col index are of length N and Z, obviously because we require, right? V and col index. So V is the and contains the non-zero values.
Value. Yeah, value.
Yeah, no, V is val and col. Yeah, V is value and col index is the column index. Contains non-zero values and the column indices of those values respectively.
So it is like, say that you have 3 cross 3 matrix and it says an identity. Then you will say like 1, 1, 1, which goes into value, and column index is 0, 4, and 8. Sorry, column index is 1, 0, 1, 2, and row index is 0, 1, 2. Right? That's how.
Yeah. No, so here it's a bit different because so what we do is col index contains the column in which the corresponding Y. I think I'll just maybe create one online, say online matrix.
Yeah. You don't have it installed, huh? I think even you have Python, no?
No, I just want to show something graphically.
Okay.
So say you have 1, 0, 5, 0, 0, 0, 3, and 0. So as per what you call, how many non-zero entries are here?
4.
2, 3, 4, right?
4.
So how will you store it? So it's like number of N and Z value is how much? N and Z?
So number of non-zero values is 4.
Yeah, 4, right? So, and in call index, what we'll do is we imply that there is in CRS, there is this article implication that we imply that there are no rows which does not have at least one non-zero value.
Okay, which means every row has a value. Okay.
Okay, so it's like you cannot have this matrix.
Yeah, I mean that's what every row has a value. You just negated it twice. So
yeah, every row must have at least one non-zero value. So how we store is we'll store 1 as value and 1 as column index, then 4 as value and 2 as column index, and then 5 as value and 1 as column index.
Yep.
0, and then again we go to 3 as value and 2 as column index. But you see, but where is row? Why is row not stored?
I mean, he stores row as well, right? In that he is given.
No, that's the thing. In CRS, we actually don't store row. Okay. Although here he mentions it, but what we essentially do is we imply that we know the length of the row, right? Oh, sorry, length of the row. So it is 3. So say we have 1, 2, 1, 2, isn't it? Yeah. So there is where so there is where we see that 1, 2, 1, 2. So we know that once it reaches, it's anything greater than 3, right? If say 1, 2, and if it comes back again 1, it means that we are in the second row.
But that's true. I agree. But
yeah,
this 4 can be in 1, 3, right?
Which one?
The 4 you wrote.
This. But there's 1, 2, right?
1, 3.
So this is 1, 2. Yeah.
It's true. What I'm trying to say is that can be in the next 0 में हो सकता है. Suppose ये तो 0 डाला, 4 0 डाला. Then you put it in the next.
So box. You put here And we put here 4.
Not
You
there,
mean
not
this?
there, not there, not there. Upper. Next one.
You mean here?
Huh? You put 4. Huh. So with this logic, now you'll get what you get. You get 1.
1, 3, 1 again.
Get 1, 3, 1.
Yeah. So it still implies that you have this 1, 4 is in the first row.
Okay. Good.
You got right?
Yeah. Cool.
Yeah. So that is the. So the implication is there are no no row which does not have at least one non-zero element, because that is implied. Anyway, the thing is, why will we solve any matrix with all rows with one row entirely 0, right? It does not make sense.
Yeah. It's
like non-invertible matrix.
It's like more solutions, right?
Yeah, no solution. It's like what to call, may or may not have solution also, and it's non-invertible matrix, so that's not what we should solve for. Right, so let's look at what how do they how do they store? Let's look at that. Yeah, the array row index is of length m+1 and encodes the index in V and call index where the given row starts. Okay, so row index is of length m+1 and encodes the index in V and call index where the given row starts. Right, so this is equivalent to row index j encoding the total number of non-zeros above row j. The last element is n and z, that is the fictitious index in V immediately after the last index. Okay, so say we have the matrix 5 0 0 0 8 0 0 0 0 3 0 0 6 0 0, right? Is a 4 cross 4 matrix with 4 non-zero elements. So here V is 5 8 3 6 and call index is 0, then 1, then 2, and then 1. And row index, what they have done is they have said that, okay, so for the first element it is 0, and 8 comes in the first row, isn't it? So F is 0 row and 8 is 1, and then 3 is row number 2 and 6 is row number 3, and then one more additional, this one 4 is just happens because we are storing m+1. So even if m is equal to 4 here,
why is he putting that 4 finally?
Yeah, it's just the thing is this row index is in general always redundant because everything can be determined just from here.
Yeah, but
we only
but observe, he's saving row index just so that, right?
Yeah, you see, right? Having 0 1 2 3 4 does not even make sense. It's like it's already implied that this is row 1, this is row 2.
No, Krishna, because actually, we also if you this I completely agree with what you're trying to say, and it is implied. मतलब 0 1 है, फिर से repeat, मतलब 1 आ गया या फिर 0 आया, मतलब we know that okay, that as soon as the next index starts,
because there are some checks going on, some if-else conditions, right? When you store, when we try to extract it.
If you save an additional array now.
So here, how will you look is there are 4 non-zero entries, right? And then we have given that the matrix size is 4 cross 4.
No, so, I'm agreeing, Krishna. I'm not saying no to you, but what I'm trying to convey here is, if you save this additional row index now, then in the algorithm, you can eliminate a lot of if-else conditions, and if-else conditions are not good in computation. Yeah, that's true. That's why if you save no additional row index, I mean, it's memory, but I think that I don't know how it actually works. I mean, you should actually do that.
So what they do is these are just like markers of every element. So we just say that there is row 1.
Also, no, then you can you'll always becomes much easier. Like okay, row index.
Yeah, that's true. I understand. Yeah, I got you.
I got you. Completely true. Row column index itself is enough to, because we are already saying that every row has to have an element.
Right. Yeah.
Yeah. Anyway, so he's saving it. Let us move ahead. It looks really interesting.
Yeah. So it's like So
to extract a row, we first define row start, row end, and
you see, right?
Exactly. So if you say from 0 to 1, Okay.
So it gives us the number of how many elements are in one particular row. So say if there were two non-zero elements, right?
Yeah.
Then we would have 1, 1 again. So 0, 1, 1, 2, 3, 4, something like that.
No. You know in the so in the first row, if you have two elements, then you have 0 and 0, right?
Okay, let's go back to our example problem. So it's like say if we have this one, right?
Yeah.
So in this case, it will be row index will be 0, 0, and then 1, and then it goes to 2.
Correct.
That is what goes on here. Yeah.
So if you want to get the elements of full row, then what you'll do is row index. You take row index.
Row index
0.
and then row index plus 1.
So if you want 0 with 1, then you'll do 0 to 1, and you row index.
So it gives us how many what you call row we have. It's like something like that. Yeah.
But if you have what the hell is faulty?
Yeah.
It looks faulty, no? Do you agree with me? I don't know. I may be missing something here. If you have three
here
elements,
actually.
If you have three elements, then how does this work? If you have three elements, then 0 and
exactly.
0 plus 1, right?
Exactly.
That's what I'm
Yeah,
thinking.
exactly.
You got me? You got the same question, right? You got the same question, right? Yeah. That's what.
So it's like this example is very specific, it seems.
No.
We should have.
Maybe what he means is, so row index 0 0 0 0 हमको चाहिए तो 0 plus 1, but 0 plus 1 is 0 again. Okay, you got row start, row ending, then you go there and it will be 0 is to 1, doesn't work. कुछ तो गड़बड़ है भाई.
Yeah, exactly. This is not very generalizable. So it looks like first we also have to count. Yeah, we also have to have a count of how many rows we have. Yeah. So it's like we always need to do this, that row index of row plus call index. Then we'll get which element this is 5 is. So if there are say 5 non-zero elements in 4x4, then it will be this will be 5, this will be 5, and this will be 6. The row index as per their what do you call format. Yeah, this is like the most commonly one used, but others then we have also compressed sparse column, and others there are several such different approaches of storing, but the most common one is
SciPy है क्या देखो, he gave a lot of libraries नीचे. Go down.
Yeah, SciPy is there.
SciPy is there. Okay, good. SciPy नहीं है. Okay, SciPy is what you need. Okay.
Yeah, and again is also here. Yeah.
Good.
Again is also here.
Again was so far, I mean, very famous in 2014-15. I mean, I don't know if people should use it, but now I don't know. I don't know what people are using anymore. Yeah, Tilinos is something very famous now. Armadillo is also very famous. I know Armadillo. I know. Yeah.
The issue is, it's like again it happens to be serial package, right? So that's the issue that we cannot. Doesn't make sense to incorporate in large codes
anymore. Yeah.
It only helps us to do some simple problems. Yeah. Or maybe problems for which is very tough to parallelize.
So again, 3 is headers only library. That's what you just put install karo header, compile minus include khatam ho gaya. You program.
So and coming back, so we're like here, right? Yeah, we were here, yeah. So that is what, so it's CRS we have understood now by now that how it's stored. And then to every extent, then we have mat abstracts the matrix data layout from the code. I hope you are,
Can't you hear me?
Yeah.
Oh wait, you are muted. Okay, fine.
Yeah. So it's like, yeah, so petsc. Now we come to our solution styles, right? How to actually use it. So so for several interesting iterative numerical solvers, we do not need to store A directly, and we would like to define functions that mimic several aspects of the operator, such as matrix vector multiplication. In petsc, this concept is called a shell, and by the dynamic polymorphism of the mat object, we can compose a shell mat at runtime. We will look more into details of how A is implemented later, but for now, petsc thinks of it as our linear operator, and so should we.
Okay.
So let's start. So it's like number of nodes in each direction, excluding those at the moment. Say n is equal to 32. Then we construct h is equal to 1 by n plus 1. These are like just the grid spacing. Then we construct A is equal to petsc dot mat dot create. So it's like we have initiated certain matrix operator, right?
Okay.
Yeah. Okay. So we have initiated certain matrix object. Now what we do is A dot set sizes. Then we are defining the size of matrix A. And in the beginning, we learned that we are solving this for a 3D problem, isn't it? That's what was mentioned. So the Laplacian in 3 will become in this form, right? N cubed, comma n cubed. Now A dot set type, then we have Python shell is equal to del.
What is Python? Why is it writing Python?
Yeah, this I think we need to know why this, what exactly this is. Yeah. Then shell is equal to del to mat, which is the cell contact, and what it says that we have to define functions. We would like to define functions that mimic several aspects of the operator. Then A dot set Python context shell, then A dot setup. It's like very hi-fi language. I think we have to deconstruct it. Let's see. So petsc vec object is a generic element of a discrete vector space. Scalar elements of the vector are distributed along processes in the same manner that mat rows are, and it supports many common mathematical operations in conjunction with the mat object. To every extent possible, vec abstracts parallel array layout from the code. X comma b is equal to a dot get vex, and then what we do is set the initial guess value to 0, and then set the right side to 1.
Okay.
Okay. So now let's come further. What is the detail? So we could create our x and b vex independently of that. Since it has already been constructed, we can use its get vex method to build them for us. In the past, the petsc developers were a little sloppy with the choice of verbs such as get, create, set, replace. Get vex would probably have been create vex and may get renamed to this in a future version. Okay. Now this is the problem with open source codes, right?
Yeah.
Yeah, and then petsc KSP object is a generic solution strategy for a system of linear equations. The KSP object supports serial and parallel, iterative, and direct linear solvers. The name comes from Krylov subspace what we're referring to, which refers to a collection of vectors spanned by the space B A B A square B till A and B, which is the basis for many iterative methods. To every extent possible, KSP abstracts the solver strategy from the code. Now, how do we set up Krylov solver? Our next step is to choose, because we use Krylov solver a lot, and we learned that during some of our Phoenix tutorials, right? Yeah. So our next step is to choose a solution scheme for solving the system of linear equations. If we do not set a type by default, petsc will utilize the GMRS or GMRES method. But since we know our system is symmetric, we select the conjugate gradients algorithm CG for better performance. So KSP, we have initiated the solver petsc.ksp.create, and then ksp.setType, which is conjugate gradient. Now, since we have a shell mat, most of the interesting preconditioners that rely on access to the mat data structure won't work. So we turn the preconditioning off. So ksp.pc, and pc is preconditioner, and we set it to be what you call none. So we are not using any preconditioning. Finally, we inform the KSP object of the operator we are solving for. We could get an additional preconditioner operator here if we like. Then use the set from options, which allows us to override the options set here from the command line. So KSP.set operators A ksp.set from options, then ksp.solve b comma x. See, that's how you solve for the matrix.
Okay.
And in Poisson's 3D demo contains two examples of syntactic sugar that should be noted. First, this function called to numpy.mgrade. I think you have shown me, right? Once you had typed something, use this command, right? mp.numgrade, mgrade.
Yeah, it's like create secret space points.
So now it's distributed mesh and all these are the other ones. Yeah. Putting it all together. Let's see what is written here. Is there more such no. Okay. What is in HTML?
They're comparing time also, na? Okay. They're comparing the time taken by petsc and other.
Yeah. I think where was it?
Yeah, here. Scaling.
I see. It's like for different segments, what is the efficiency? Okay. So let's look for some example problem, petsc examples maybe. I think that will be help us to get an idea. I'm sure there must be some good posts written on this, isn't it? Let's get to back to let's take a look at some of the petsc uses. So petsc is widely used. Okay, so here is one of such examples. So let's see what they have done here, isn't it? This sounds to be a very nice lecture series, huh? High performance computing with Python.
Okay.
So let's see what they have solved here. So the main object in petsc for creating sparse matrices is the mat object. That's what we learned. Typically, we create a sparse matrix in 3 steps. We first specify the layout of the matrix, then assign the matrix elements, and then assemble the matrix. petsc by default uses CRS matrix format and distributed rows across different compute nodes. In this example, we do not use the parallel features of petsc and refer to the documentation for details. Let us get started and specify a matrix of dimension 1000 cross 1000. We want to have a tridiagonal matrix, so we'll have 2 entries in the first and last row and 3 entries in each row. Okay, petsc can dynamically grow sizes needed to store matrix entries, but this is inefficient and it's useful to pre-allocate the storage size. So from petsc4py, we import petsc class and import numpy as numpy, then n is equal to 1000. Then we define n and z as number of non-zero elements, right? Non-zero entries, and this happens to be 3 into np 1000. So we have defined 3000 non-zero entries. D type is equal to np dot integer, 32-bit integer. The n and z 0 is equal to n and z minus. So the first and last element is 2. Now we create a is equal to petsc.mat. We have initiated this a operator, and then a dot create aij. I think this is like you are building the matrix, right? This is what it implies, right? That's how we write matrix, isn't it? aij.
Yeah. But why does he have like 3000 elements? Okay.
Yeah, so 3000 elements are non-zeros.
10 power 6 is total elements, but only he has 3000 elements he's considering as.
Exactly, yes. Yeah. And so once we prescribe this, then it knows how to construct it. Yeah. N comma n, and then n and z is equal to n and z. So that's how we have actually initialized something, specified the storage of this matrix. Now we fix the matrix element as a dot set value 002, which is 00 is the first element, isn't it? And 2. And the a dot set value 0 comma 1, which is like the second element in the first row, right? 0 1 and fill it with -1. It's like we are just trying to construct that tridiagonal matrix, right? Something of that sort, like that tridiagonal matrix. Then for the last row we have 998, 998 -1 is the second last element in the last row, and then 999999 is the last diagonal element. Now for index in range 1 n -1, we are just doing all this. Yeah, it's like we are just having 2 -1 and then -1 2 1. So that is our banded matrix. Now we can assemble the matrix. This lets petsc create all necessary internal data structures. And we now have petsc matrix to our disposal. Let's try some commands. A.size is 1000 cross 1000. Get the local size is the storage in the current process only relevant for parallel operations. Check if the matrix is symmetric. Yes, it is symmetric. A dot is symmetric. There are lots of convenient functions to access matrix elements. For example, to get the diagonal elements, we can do the following. Diagonals is equal to a dot get diagonal dot array. So this will give us the diagonal elements, right?
Okay.
And then print diagonals dot shape will just give us the shape because it will be a 1D vector. And get memory information from the matrix a dot get info. Then this gives us all that sparse, right? All the information, block size 1, NZ allocated 2,998, use 2,998, needed 0, memory this much, assemblies, mallocs, fill ratio, and all such things. Then we can return the data structure associated with the CSR matrix. So it's like index pointer, indices, and data. So this will help us to get. Now we now want to solve a linear system of equations with this matrix. So the basic solver object is KSP. So we initiate that petsc.ksp.create. We need to let KSP know about the operators. So KSP.set operators A. And we need to define our right hand side. Is important to choose vectors that are compatible with the data distribution of A. So let y is equal to x. Then to get the data distribution for A, we need A.create vec left. To get the data distribution for x, we need to use A.create right, create vec right. So these are like b is equal to A.create vec left. And to get it, and so in this form, then only it makes sense, right? So it will be b is equal to ax. Then only we'll have b is equal to A.create vec left. And the following initializes the full solver and solves the problem as iterated solver which choose by CG step. So by CG step is by conjugate stabilization with stabilization. So this is like yeah, if our matrix does not happen to be symmetric in nature, and we still want to use the features of conjugate gradient. So conjugate gradient is a method which can be used only to solve linear algebra problems in which A happens to be symmetric in nature. And so, and it's a very efficient approach. So, and if our matrix does not happen to be symmetric, and we would still want to utilize some very efficient functionalities in this CG approach, then we use by CG. It means by conjugate stabilization. Yeah, we will discuss it someday. Yeah, it's like I did a little bit. I haven't understood all these methods, so we'll discuss it someday again. And it is an iterative solver for non-symmetric equations, systems of equations that requires only a short recurrence, and therefore, in contrast to GMRS, need not to store the whole Krylov subspace basis. That is disadvantage is that it does not guarantee that the residuals is minimized in each step. So there is a very nice book on all such methods that is known as iterative solvers for something systems. Let me just. It's written by what was his name? I forget. Let's open it. Some Yusuf Saad. Iterative solvers. Yusuf. I hope this is the name. Yeah, Yusuf Saad. Yeah, this is a very nice book actually on linear algebra.
Okay.
In fact, you can say one of the best books.
Okay.
That is from an applications point of view. As an engineer, we require from an application point of view, right? Something which can be implemented on a computer system. So he gives us both details. The fundamental applied mathematics, because he happens to be an applied mathematician, Yusuf Saad. So you see background linear algebra, all the fundamental. I think this is something we should actually discuss in our meetings here. So lists like the background linear algebra, the complete, then you have discretization of PDEs, sparse matrices. So ultimately, graph theory is very much used in sparse matrices, all those adjacency graphs and all that, isn't it? And then basic iterative methods, convergence approaches, then projection methods. Then you have Krylov subspace methods. You see, right?
Yeah.
And all you have Arnold's approach. So Arnold algorithm is, I think, used to sorry, the Lang's algorithm is used to compute eigenvalues. So even the computer solves for eigenvalues, you must know that those are not the true eigenvalues. They are just an approximation, approximated eigenvalues. So a solver is only able to give us clear picture of the lowest eigenvalue or something of that sort. The rest are all approximations here. And we don't actually solve a polynomial matrix. That we don't solve a characteristic polynomial to get eigenvalues, because to solve for the roots of a polynomial is a very, very unstable approach actually.
Okay.
The thing is, say if you have say you have say x square minus 2x plus 1 is equal to 0, right?
Okay.
Theoretically, the answers are 1, 1.
Yeah.
Now, say you just perturb the coefficient. Say you have x square minus 2.001 x plus some 0.999.
Okay.
And you solve it. So you will say, come on, the answer should still be very close to -1. Sorry, 1, 1, right? You will be surprised to know that it's not the case.
Okay.
Or maybe let's just try to use MATLAB. I think it helps us to get what we call. Why don't I use online math?
No, so Narendra K. Someone joined actually. I don't know. Hi, Narendra. Narendra K. This meeting is can't. Anyways.
Say some. Maybe just let's just try if it gives something. Say we have so roots. That's what we do, right? Roots of something.
Yeah. Yeah.
Run.
So there is this. I have seen this thing. Not this one. You know the approximation, right? Like 1 plus something power something. So you expand it using some series, right? You think that as you keep on adding extra terms, it will get converged. But no, after some point, it starts to diverge.
You see, right? The variance.
Okay. Yeah.
I'm just maybe just have 2001, 201, and then let's have say 99. Just 1% of error. See that the difference you see, 1% of error has created almost 14% error in the eigenvalues. You see, right? So say what if 1% error is there? Sorry, 10% error. Yeah, it just went haywire, 50% error. So that is the issue with using this root finding algorithms to solve for eigenvalues. That's not an approach to look for. Okay. And then you have this Krylov subspace, then all the approaches. And then we have what you call the Krylov subspace methods part 2. Then you have methods related to normal equations, precondition algorithms. So this is where we are looking, right? What was preconditioning of system. Now you see preconditioning techniques. Now you see there are several preconditioners, Jacobi, successive over-relaxation methods. Then you have ILU, which is incomplete LU factorization, zero fill-in, threshold strategies, and approximate inverse preconditioners. And then we have block preconditioners. Then you have preconditioners for normal equations. So this is like a very comprehensive details on preconditioning schemes. And then you have parallel implementation, how to do it on a set of vertical on a parallel system, right? And you have these two different formats also to store CSR and column storage, compressed storage column, and parallel preconditioners, domain decomposition methods. So this is the best book you can have on implementation of what you call numerical algorithms for linear algebra. It's meant to be a reference book. The author has talked about everything in quite a detail, very much from an engineer's perspective. Yeah. You see, right? Everything he goes, explains, and then he goes into
our numerical techniques as well.
Yeah.
Method and
yeah. So it's like a very good book.
That sparse matrix figure he also put now. The sparse matrix figure he उसने भी लगाया.
The thing is, this is a very common, like whenever you want to visualize sparse matrices, right? So that is how you visualize. So this is known as, this gives us an idea about the sparsity. It has a name. I forgot its name. There is a name of this matrix of this graphic representation. It's a very nicely written book, man. It's quite good. And the good thing is everything is in one place. We don't need to run here and there to get complete picture. Everything is in one place. Coming back to our guide. So I think we were here. So we initialized the operators, then we created B matrix, and then we don't want preconditioner, because many a time if we are not using a proper preconditioner, right? Rather than improving convergence, it can in fact slow down the convergence also. So it's so that's the reason that selecting a good preconditioner happens to a very hit and trial approach. And also it comes gradually with experience, or requires some intuitive thinking as to which precondition we should choose. So once we have defined this X where we are going to solve for, then KSP will call the petsc.ksp create ksp.operators A. Then set type, we are using biconjugate gradient approach. Then we are set the convergence history. Then get preconditioner, set type none. And now we solve for ksp.solve b comma x. Once we do that, now we can we can also store the convergence history, right? So residuals is equal to ksp dot get convergence history, and then we are able to solve. We are able to plot it. So you see how it's. You see in between, right? It does not monotonically decrease. It even shoots up for some time for certain iterations and then returns. Like here was one shoot, and here actually it reduces and then again shoots up, and then this is the thing with such biconjugate, but eventually it does reach some particular certain convergence criteria. So if you use some preconditioners, so here we had require how many iterations to converge to 10 power minus 4? 500, right?
Yeah.
Now you see if you use successive over relaxation method as preconditioner, so then what we see is it converges
175
in 175 iterations. See. And we can also, if you want to use a direct solver with petsc, we need to specify the direct solver as preconditioner. Tell petsc to only evaluate this preconditioner. This I cannot really understand, but yeah, it's like trying to do some direct solution approach. I think this happens. This is a very good what do you call lecture series. I think we can start from here. We are solving this, right? We discretize everything is done. Defining this. First, he uses some what you call inbuilt functions. I mean functions from SciPy and all, but you know these are not effective way of doing things, right? So that's why we go to all these petsc libraries, because those are much more computationally efficient. So maybe I'll share this link, right? I think this happens to a very good collection of all the ideas in computational linear algebra. And there are also assignments to do.
So much content these days online.
Yeah, man, and most of the good content are always in terms as some blog series like this.
Somebody's
happens to be some
and they wrote right. Somebody frustrated and like I will write something nice and you sit on it.
Exactly. Yeah. This is a nice tutorial. I'll just share in the chat window, chat box. So should we? I think maybe I'll stop sharing screen. Let's go back to our. Yeah. So should we discuss one paper, or what do you suggest? Okay. So should I stop the recording or let it continue?
I think you already stopped. I think.
No, it's not. It stopped. I just stopped sharing.
Stop then. Stop.
Okay. So yeah, let's meet next week. Yeah.